Good afternoon. So section 7.3. Trigonometric substitution. Okay, so I will motivate by trying to solve the following problem. Let's suppose that we have a circle of radius A, okay, with a center at the origin, and I want to evaluate the area of this quarter of a circle. What's the answer?
1.5.
So this is the answer, right? Okay, so we'll keep that in mind. And now we go to do it systematically by calculating the area of this object. Right, so we can set up our usual integral under a curve. So the area is going to be given by an integral from 0 to a y dx, right? So this is y. We need to find the formula for y. So how can we express this curve as a function of x? Well, we know that x squared plus y squared equals a squared because it's a circle. And we can resolve it for y because we're in a positive quadrant. We have no doubt about the sign of y. It's positive. So this is square root of a squared minus x squared, right? So my formula for the area becomes the following definite integral. Okay. So this is what I need to evaluate. Is this an easy integral? So we've seen something like this, and in principle we could try to do substitution, right? We can say that this is u, okay? du dx is something like 2x, but there's an x missing from here, right? Usually such integrals involve times x dx, in which case we have a signature of the derivative of this additional variable. Now we don't have that, so this method of substitution will fail. And we have to find a different method. But luckily here, we have the geometry working for us. So let's consider a certain level x, okay? And this is y as a function of x. Okay, so and this is a, the long side of this right triangle. Let's denote this angle theta. Okay, and I'm going to express y and express x as theta. So what is the relationship between x and theta? We can say that x is a times cosine theta, correct? Okay, so and this is a substitution that I'm going to use for this integral. So let's just play with it a little bit. Let's say that when x is equal to 0, what is the value of theta? x0 means we're here, right? So what is theta? 90 degrees, or pi over 2. So we can say that theta is pi over 2. When x equals a, because I go from 0 to a, x equals a means that I'm here. What is theta? Is 0, right? This whole thing collapses into a straight line. So theta is equal to 0. You can also check it here. For instance, x equals 0 corresponds to cosine of pi over 2. Cosine of pi over 2 is 0. X equals a corresponds to cosine being equal to 1, which is theta equals 0. So this works. Okay? And finally, I want to calculate dx, the differential. So I have to differentiate both sides of this equation. So I have a times minus sine theta, d theta. And now I'm going to try and rewrite this whole thing in terms of theta. So I go from the x-coordinate of each point to its angular coordinate. It's kind of like going to polar coordinates. So for 0, I have pi over 2. For a, I have 0. I have square root of a squared minus a squared cos squared theta. And for dx, I have this whole expression times a sine theta d theta, and I shouldn't forget the minus sign, which appears in front of the integral. Okay. So now this is my new integral, completely rewritten in terms of the angle. And I can do things here. For instance, I can see that under the square root, a squared multiplies both of the terms. And also I can see that pi over 2 is greater than 0, and I have a minus sign. So I can flip and lose the minus. So I have from 0 to pi over 2. Okay. I have square root of a squared 1 minus cos squared theta. I'm going to do it like this. Times a sine theta d theta. What else can I do? A is a radius. It's a positive number. So I'm going to take it out. In fact, I'm going to take this a and this a out, like this. What do I have under the square root now? 1 minus cos squared theta. Can I simplify this expression? Yes, of course. This is sine squared theta. So under the square root, I have sine squared theta. Can I evaluate this expression? Square root of sine squared theta. Well, in general, it's plus or minus sine theta. But because I'm here, I know that theta is positive, and its sine is also positive. So I can, with confidence, replace that with sine theta. So here under the integral, I have sine theta times sine theta d theta. Okay? Or rewriting it again. Okay. So I reduced this integral, which I didn't really know what to do with, to this integral, which we looked at yesterday, the day before yesterday, right? When we looked at trigonometric integrals, an even power of sine. In this case, we use double or half angle identities, right? We can rewrite sine squared theta as 1/2 1 minus cos 2 theta. Okay. So I have a squared over 2, and integral from 0 to pi over 2, 1 minus cos 2 theta d theta. And this integral I can definitely evaluate. So continue here. I have theta minus 1/2 sine 2 theta, evaluated from 0 to pi over 2, right? This is my antiderivative. Questions so far? We're almost done. It's easy from now. So a squared over 2. So I have pi over 2 minus 0 minus 1/2 sine. So instead of theta, I substitute pi over 2 times 2. So sine pi plus sine of 0. What happens to sine of pi and sine of 0? They are, of course, 0. And I can write down the answer. Which is this. And then I go here. And good news, it's exactly as expected. right? So this is just to check that the calculation holds. But the lesson from here is that we used a very sophisticated substitution in this case. We said that x is a trigonometric function. So we reduced an algebraic function to a trigonometric function here. And then we're able to simplify it enough to be able to evaluate the integral. Okay? And this is the principle that we'll use over and over for integrals of this sort. They don't look trigonometric, but we can make them into trigonometric functions. So as the first example of this that is less trivial, where we don't know the answer, right? We consider the following integral. So let's make it an indefinite integral. And we have 25 minus x squared dx. This example is a little bit harder than others. Okay, so it's not always going to be that long, but it illustrates a number of points. So I wanted to do this. So what I notice is this combination is similar to this combination, okay, under the square root. And I'm going to take advantage of this. Let me just grab the notes. Over here, I'll start a table that gives us a recipe. Okay, when we see a certain pattern, we use a substitution. So here, in this case, I can use cosine or sine. So the book suggests to use the sine. It doesn't matter. So let's say that x is a sine theta, okay? And I want to restrict the range of this function, the domain of this function, or the range of theta, to this. And I'm going to use an identity. 1 minus sine squared theta is cosine squared theta. Okay, so let's see. Here we have this pattern. I'm going to take x to be equal to 5 sine theta. And you'll see that it helps tremendously. The question?
Why is it sine?
So over here I used cosine. And the cosine would work just as well. This is my own example, and it's motivated by the geometry. Okay, so that's why I did it. In the book, they suggest this choice, but it really doesn't matter. You can use either. So here we can say or, okay, x equals a cosine theta from 0 to pi, and we use the same identity. Okay, either or will work. Let's now when we implement this, you will see immediately what advantage it gives you. Okay, so first of all, let's substitute this into the square root. So we have 25 minus 25 sine squared theta. You will see that it immediately simplifies this. Okay, so we can take the square root of 25 out. That gives me 5. And it's 1 minus sine squared theta, which is 5 square root of cosine squared. And because of the choice of the domain, I can rest assured that this is a positive quantity. So it's simply 5 cos theta. So instead of the square root, after this substitution, I end up with cosine. And it's a lot better. Okay? As long as I can take care of the rest. And let's see how this is done. So I have to take care of the differential. So what is dx? This is calculated simply from the definition of x. I have 5 cos theta d theta. And now I'm ready to perform the substitution and express everything in terms of theta. So the square root comes from here, and it's just 5 cos theta. X squared is given by 5 squared sine squared theta. So this guy is just x squared. And for dx, I substitute this expression. 5 cos theta d theta. So everything is sines and cosines only. And let's see if we can simplify this to make this doable. So how many 5s do we have? 1, 2, 3, 4. So I get 5 to the 4th. Okay. I have 2 cosines, and I have 2 sines d theta. So I wonder if this is doable. What do you think? Question?
So is A equal to like the...
A is the number that appears under square root squared. So here, for simplicity, we have 25. So it's easy to take a square root. But it could be any number. You just take a square root. If this was 10, I would use square root of 10 here.
Okay.
Right? It has, because when squared, so I use x squared. So this number has to match this.
Or, yeah, but then, I was wondering how the 5 cosine theta, why that shows up twice.
So this one comes from the square root. So this is really square root of 25 minus x squared, right? This guy is x squared, and this is dx.
All right.
So these are the 3 components: the square root, x squared, and dx. And each of them brings some trigonometric functions. Okay. So can we take this integral? Well, yeah. So we're going to use the identity. Do you remember this? Sine 2 theta is 2 sine theta cos theta. If I square this, I get sine squared 2 theta is 4 sine squared theta cos squared theta. So I'm going to use this divided by 4. So I get 5 to the 4 over 4. And I have sine squared 2 theta d theta. So I reduced this to sine squared, which is not the end of the story yet. I want to have a sine or cosine, not squared. So another identity comes here. I express this as 1/2 1 minus cos 4 theta. It's another half angle identity. So you see, this is material of the previous lecture, where we have even powers of sines and cosines, and we keep using these half angle identities over and over until we're done. So here I have to use it twice. 5 to the 4 divided by 8, 1 minus cos 4 theta d theta. So this is doable now, because everybody knows how to integrate cosine of 4 theta. So let's write down the antiderivative. 5 to the 4. What's going on? So I have theta minus sine 4 theta over 4 plus c. And normally I would be almost done, okay? Because what is left? I have my antiderivative. All I need to do is to go back to the original variable. So here, with these trigonometric substitutions, sometimes this is a hard step to take. With regular substitutions, this is very easy. But here, you see, the problem is that here I know sine 4 theta. And the definition of my substitution involves sine of theta. So how do I express sine 4 theta in terms of x? It's not, so I could use arcsine. So let's play with this a little bit. So do you guys have questions about this? You're totally noisy. What's going on? Questions? Okay. So what I'm going to draw is the definition of theta. what do I know about theta? I can draw theta and draw a right triangle. And the definition is such that x equals 5 sine theta. So what's the easiest triangle that satisfies this property? So sine theta is x over 5, right? So I want to make this x, and I want to make this 5, and then this is correct, right? This is the easiest way to achieve this. Now, all I need to do is calculate this side, okay? And I can do this. It's 25 minus x squared from the right triangle. So now I know quite a lot of things about theta. I know its sine, and I also know its cosine. What's cosine theta? This is going to be this side divided by 5. So it's 25 minus x squared over 5. What I need to calculate is sine. We need sine for theta. And I know sine theta. Okay, so let's write it like this. Sine for theta is equal to 2 sine 2 theta cosine 2 theta. I'm using a double angle identity again, right? You remember that. That double angle is double sine is sine and cosine. And now for this one, I'm going to say 2 sine theta cos theta. And for this one, I'm going to say cos squared theta minus sine squared theta. If you don't remember them exactly, they must look familiar somewhat. You should be aware of the fact that cosine 2 theta can be expressed in terms of sine and cosine of theta, and the sine also. So this is done by these formulas. Okay. So let me put them all together. 4 sine theta cos theta times cos squared theta minus sine squared theta. So now the object that I'm after is completely expressed in terms of sine and cosine of theta, and they're all here. They're all in this right triangle. I know the expressions for them. So let me continue writing here. Oh, and finally, I want to express theta also. From this, I can say that theta is equal to arc sine of x over 5. Okay? So I'm ready to write down the answer. 5 to the 4th over 8 arc sine of x over 5 plus, minus minus 1/4 times 4. So I have sine theta cos theta cos squared theta minus sine squared theta equals, almost done. So sine theta, I read it off of there. Sine theta is x over 5. Cosine theta is square root of 25 minus x squared over 5. And let me do this one separately. So I have 25 minus x squared over 25 minus x squared over 25. So it's 25 minus 2 x squared over 25. Plus c. Well, I can potentially simplify a little bit more. Okay, this is 5 to the 4, and this is 5 to the 4. So I have 5 to the 4 over 8 arcsine of x over 5 minus x over 8, 25 minus x squared, 25 minus 2x squared plus c. So this is the final answer. Question?
What happened to the 4?
This 4 cancels with this 4.
I'm sorry, which identity did you use to substitute for cosine of 2 theta?
This one. So the cosine I know from the triangle. Was that the question? How do I know the cosine?
No, it's how did you substitute cosine of 2 theta into cosine squared minus sine squared?
So this is identity. It's just like this. Cosine 2 theta is cos squared theta minus sine squared theta. This is something I remember. And well, it's better if you remember this too. So there are 2 of these, only 2. Sine 2 sine theta cos theta. So there are 2 identities that come up all the time. Okay, so I suggest that you memorize them if you don't know them. So here I actually had to use both. Okay, so the next example. What's going on today?
Can we slow down?
Ooh, okay. So this was a brutal example, is what you're saying.
Of course.
Okay. So how about if I post this? Okay, so you have it online. Because I have to move on with other examples, otherwise we will never catch up. So, okay. I promise this one will be easier. Okay. So how about this one? So in this example, we again have a square root. And it also involves x squared under the square root. But it is not exactly this kind of a pattern. Okay? Instead of minus sign, we have a plus. Question?
Just a quick question. Where did the sine 4 theta go? Where did the divided by 4 go?
So this can't, oh, it's erased. This expression had a 4 in front of it.
Oh, it did.
This exact expression had a 4 in front of it.
Oh, right.
Okay. So let's not worry about that example. I will post it. So now, if you want to write down that pattern in general, so what do we see? It's something like a squared plus x squared. Okay. And it requires a different technique, a slightly different technique, and a different identity. So here, we're going to take x equals a tangent theta, okay, between minus pi over 2. Oh, sorry, it's strict identity, strict inequality. And we use the identity 1 plus tangent squared theta equals secant squared theta. Why do we use this? Because this identity has a plus. Okay, this identity has a minus. So this is the difference. So let's try how this works. So I'm going to set x equals 2 tangent theta. Okay, and see what this gives me. So the first step is to substitute it under the square root to see if it helps me. So I have 4 tangent squared theta plus 4. So 4 comes out to give me 2, and I have tangent squared theta plus 1. So that's the identity. Okay, it immediately comes in here. So I have 2 square root of secant squared, and because it's guaranteed to be a positive quantity by the restriction of theta, I can simply say that this is a secant. Okay? So this square root simplifies tremendously. I just have to see what happens to the rest of this integral. So dx, so x squared is easy, we express it from here. Dx can be just calculated. So I have 2 secant squared theta d theta. And I'm ready to rewrite this. So let's say 2 secant squared theta d theta. So this is dx. And in the denominator, I have 4 tangent squared theta. So this is x squared. And I have 2 secant theta. This is the square root. And you can see already that something is going to cancel. So what cancels? 2 cancels. So I have 1/4. Secant cancels. And I have tangent squared at the denominator. Okay. So this doesn't look familiar, but it doesn't look so bad. In this case, it pays off to remember what secant is and what tangent is in terms of sine and cosine. So 1/4 secant is 1 over cos theta. No, actually, let me do it like this. So I have cos theta, and tangent is sine squared theta, cos squared theta, d theta. And I have one more cancellation. Cosine goes, so I have cos theta d theta, and I have sine squared. Can we take this integral? We can, actually. This one is OK. Because you notice that cosine is the derivative of sine. So we can use a regular substitution of the type that we're used to. So here, if I say u is equal to sine theta, then du is cos theta d theta. And this integral becomes very easy. I have du over u squared. Okay. So this is really nice. Integrates easily. Oh. So minus 1/4, 1 over u plus c. Okay. Now I remember what is u. What is u? U is sine theta plus c. So all I need to do is to express sine theta in terms of x. So I go here and I see, oh no, I don't know sine. I only know the tangent. So at this stage, we draw the triangle. Okay. So here's the triangle. This triangle is always based on the definition of my original substitution. So what is my original rule? X equals 2 tangent theta, or tangent theta is x over 2. So this is theta. This is a right angle. To make tangent to be equal to x over 2, I assign this x and I assign this 2. And then I calculate the remaining side, like this. So now I know everything about the angle theta. In particular, I'm interested in its sine. So I can say that sine theta is x over square root of 4 plus x squared. So here I have x in the denominator, 4x, and I have 4 plus x squared plus c. Okay. So that's the answer. Questions? So this is a lot better. So I see. So psychologically, this is the right move. First, I give you a really horrible example, and now you're going to like all the rest of the examples. Okay. So the next example is similar. Let's look at this. Oh, actually, I'm going to give you one more rule. There is one more logical possibility here. So what other combination can occur under the square root? Yes. So this, if I interchange these, it's the same. But I can also have x squared minus a squared. Okay. So in this case, I use secant, where theta goes from 0 to pi over 2, and or from pi to 3 pi over 2. These conditions, again, are here to be able to resolve the square root of square. So we want to make sure that the tangent of theta is positive. And I'm going to use the identity secant squared theta minus 1 equals tangent squared theta. Okay, and maybe I won't give you an example of this. You can do it at the discussion, because it's very similar to a previous example. But I'd rather explain to you something slightly different. Okay, so let's look at the last example. Which doesn't look like this, okay? But it has the same pattern hidden inside. So we're looking at the following integral. So if you look at the expression under the square root, it's none of the three expressions just listed. But it really is one of them. It's just hiding. One more step separates this expression from one of the three. And to see that, we're going to write down this and try to uncover a square there. Okay, I want to have something plus or minus x squared. So this is what we write. This is equal to 5 minus, and everything that involves x I put in brackets. So x squared plus 4x. So ideally I want to have a constant minus x squared. Instead of x squared I have this. So I'm going to complete a square here. I have x squared plus 4x. What do I need to do to complete this particular square? Excellent, plus 4, okay? And I have to also subtract it because I have an equality here. I cannot change it. Okay, so next I have 5. Then this 4, I want to get rid of it, so it goes 5 plus 4. And I have in brackets a complete square. Or 9 minus x plus 2 squared. So the idea is to have a constant plus or minus a square of something that involves x. Or it could be the other way around. It could be a square of x minus a constant. So it has to match one of those patterns. So now let's write it like this. And now we can work with it after one more step. So we'll make a change of variables first. I'm going to say that u is x plus 2. Okay, whatever I see here, I'm going to make this equal to u. And I need to express x. X is just u minus 2. And dx is du. That's a really easy substitution. That gives me the following. So I have u minus 2 du. And now I have 9 minus u squared. And this is what I was after. Now I reduced it to a pattern that is familiar. And we can use a trigonometric substitution to solve this. So which one is this? It's actually the first one, where I can use sine or cosine. So let me continue here. I'm going to set u is 3 sine theta. Okay, so under the square root, 9 minus u squared. What do I have? 9 minus 9 sine squared theta, which is 3 cosine theta. So that's how much the square root is simplified. So let me just do this. I have 3 sine theta minus 2 du. And here I have 3 cos theta. Oh, and I forgot the differential. Okay, we should never forget the differential. So I have 3 cos theta d theta. So that goes instead of du, right? 3 cos theta d theta. And that's very lucky because 3 cos theta cancel like this. So the integral actually turns out to be a pretty easy one. 3 sine theta minus 2 d theta. And everybody can take this, right? So let's continue. So I have minus 3 cosine theta minus 2 theta plus c. Almost done, except I have to go back to my original variable x. And there are 2 substitutions. So first, I return to from theta to u. I know sine of u. I know sine of theta. This requires cosine of theta. So I have to draw a triangle. So again, just to see why we need a triangle. This answer requires the knowledge of cosine of theta in terms of x. What we do know is sine theta in terms of u. So theta is this. From my definition, u equals 3 sorry. The definition is u is 3 sine theta. So sine theta is u over 3. So I assign this to be u, and this is 3, and this is 9 minus u squared. Okay. Therefore, cosine theta is calculated easily like this. So minus 3, 9 minus u squared over 3 minus 2. So from here, rather from here, theta is arc sine of u over 3. So arc sine u over 3. Almost done. What is the last step? To go to x, right? U is x plus 2. So all I need to do is replace u with x plus 2. And I can also cancel this number 3 here. So I have 9 minus x plus 2 squared minus 2 arc sine x plus 2 over 3 plus c. Questions? So this was a more advanced example where we have a quadratic form in the square root. And we uncover a pattern that involves a number plus a variable squared or minus variable squared. Okay? So can we always do this? The answer is yes, we can always complete squares. Okay? Because I have a couple of minutes, I want to illustrate this last pattern that we kind of skipped. Okay? I won't finish it, but I'll motivate. So let's consider an integral x cubed 4x squared plus 9 3/2 Okay. So do we have a square root here? Yes, because we have a power 3/2. It's a square root cubed. Okay. So we can use all the same rules. So let's write down what we have there. I want to take 9 out of brackets. So I have 4/9 x squared plus 1. Okay. Oh no, I think I want to take 4 out. Sorry. Okay. So now you can see that A is equal to 3/2. Can you see that? Okay. So that motivates the substitution. X equals 3/2 tangent theta. Dx is 3/2 secant squared theta d theta. How about the square root? So 4x squared plus 9 3/2. What's that equal to? I have 4, and I have 3/2 4 times 9/4 tangent squared theta plus 9/4 3/2. So I have 9/4 of 1 I'm sorry, this is just 9. 9, 1 plus tangent squared theta, 3/2. So this is equal to 27, okay, secant cubed theta. Okay, because this is secant squared theta, 3/2. So I have to take the square root of secant squared, and the remaining power is 1/3. Questions? So secant squared theta to the power 3/2 is secant cubed theta. So now I'll just finish writing this down. So x squared is 9/4 is 3/2 tangent theta cubed times 3/2 secant squared theta d theta, and the denominator is 27 secant cubed theta. And this is an integral that after a few steps will simplify enough for you to take it. Thank you very much.